Equivalent systems. Two linear systems are equivalent if they have the same solution set. Let's look at some examples. Here we have a linear system of two equations in two variables, x plus y equals 2, x minus y equals 2. And here we have another linear system of two equations in two variables. This time we have x minus y equals 2 and x plus y equals 2. These two linear systems are equivalent. Notice that we got from the first system to the second system simply by interchanging the two equations. We write e sub 1 with a double left-right arrow, e sub 2, to indicate that to get from the first system to the second system, we've just interchanged equation 1 with equation 2. Let's look at another example. X minus 3y equals negative 3, 2x plus y equals 8. This time, let's go ahead and multiply the first equation through by negative 2. We get negative 2x plus 6y equals 6. And let's leave the second equation alone. So we'll just copy that one over. What we get is a system which is equivalent to the original system. Here we've done a scaling. We've scaled the first equation by multiplying it by negative 2. We'll use the notation negative 2 e sub 1 to indicate that we've multiplied equation 1 by negative 2. Another example. Again, we have the same linear system here of two equations and two variables. This time I'm going to leave the first equation alone, x minus 3y equals negative 3, and I'm going to replace the second equation by the equation 7y equals 14. This is known as a replacement operation. Now you can't just replace one equation by anything and get a new system which is equivalent to the original. You have to follow certain rules. In this case, what we did to get from the first system to the second system is we replaced the second equation by a new equation by taking equation 2 minus 2 times equation 1. Let's see the details. So equation 2 is 2x plus y equals 8. Negative 2 times equation 1 is negative 2 times x minus 3y equals negative 3, which after distributing, we get negative 2x plus 6y on the left, and on the right we get negative 2 times negative 3, which is 6. Adding the two equations, the 2x and negative 2x cancel out to 0. Y plus 6y is 7y, and 8 plus 6 is 14. So we go ahead and replace 2x plus y equals 8 by 7y equals 14. So let's solve the second system. We're going to use a method called back solving. 7y equals 14 is easy to solve for y by dividing each side of that equation by 2 to get y equals 2. Now let's take the first equation, x minus 3y equals negative 3, add 3y to each side, and then replace y by 2 to get that x is negative 3 plus 3 times 2 equals negative 3 plus 6, which is 3. So the only solution to that second system is x equals 3, y equals 2. Let's check that this is also the only solution to the first system. Well, first of all, we already know that it's a solution to the first equation, x minus 3y equals negative 3, because those equations are the same in both systems. So we only need to check that x equals 3, y equals 2 is a solution to 2x plus y equals 8. Let's go ahead and plug 3 in for x and 2 in for y. So 2x plus y is 2 times 3 plus 2, which is 6 plus 2, which is 8. And that agrees with the right-hand side. So it is in fact a solution to the first system as well. We form the augmented matrix of a linear system by simply dropping all the variables and the equal sign. So let's look at some examples. Here's a linear system of two equations and two variables, x plus y equals 2, x minus y equals 3. And the corresponding augmented matrix looks like this. What we did is we took the coefficients of x and y in each equation together with the right-hand sides. So we have 1x plus 1y equals 2 for the first equation, That becomes the first row of the augmented matrix, 1, 1, 2. And for the second equation, we have 1x minus 1y equals 3, giving us the second row of that augmented matrix. Some people like to put a separating line where the equal signs would be in the equations, just to make it a little easier to see what's going on there. This line is optional. Another example. So here we have a linear system of 3 equations in 3 variables, and here's the corresponding augmented matrix. Notice we have 1x minus 2y plus 1z equals 0, 0x plus 2y minus 8z equals 8, negative 3x plus 5y minus 3z equals negative 7. And there's that line again if you want to throw that in. That's up to you. One more example. So here we have a system of 3 equations in 4 variables, and here's the corresponding augmented matrix. We have 1x1 plus 2x2 plus 3x3 plus 4x4 equals 5, 1x1 plus 3x2 plus 5x3 plus 7x4 equals 11, 1x1 plus 0x2 minus 1x3 minus 2x4 equals negative 6. And there's that line again. Elementary row operations. Let's look at some examples to see how elementary row operations work. Here's the first example we did of interchanging 2 equations. Let's see how this interchange works in terms of augmented matrices. The augmented matrix of that first system on the left is 1, 1, 2, 1, negative 1, 2. We're going to go ahead and interchange the 2 rows of this augmented matrix, and we use this notation row 1 with the double arrow row 2, and we get 1, negative 1, 2, 1, 1, 2 as our new augmented matrix after we do that row interchange. Notice that the linear system corresponding to this augmented matrix is the one on the upper right there, x minus y equals 2, x plus y equals 2. Okay, so this is a row interchange operation. This is our first elementary row operation. Another example. Here's the second example we did of scaling. Let's see how this one looks in terms of augmented matrices. The augmented matrix of that first system on the left is 1, negative 3, negative 3, 2, 1, 8. And we're going to apply the scaling row operation by multiplying row 1 by negative 2. So let's just rewrite the second equation since it's not going to be changing, 2, 1, 8. And now we're going to go ahead and multiply each entry of that first row by negative 2. Negative 2 times 1 is negative 2. Negative 2 times negative 3 is 6. And again, negative 2 times negative 3 is 6. Okay, so that was our second elementary row operation. This one was scaling. Another example. So that third one we did, that replacement operation, looks like this, and here's the corresponding augmented matrix for that first linear system, 1, negative 3, negative 3, 2, 1, 8. We're going to apply the row replacement operation. We're going to take row 2 minus 2 row 1, and we're going to replace the second row by the result, and that's why I write the operation next to the second row. Okay, so first, we're not changing the first row, only the second row. So we go ahead and we just rewrite the first row, 1, negative 3, negative 3. Let's go ahead and do the second row column by column. So for the first column, we have that the entry in row 1 is 1, and the entry in row 2 is 2. So when we do row 2 minus 2 row 1, we get 2 minus 2 times 1, which is 2 minus 2, and that's 0. And we go ahead and we put that 0 as the first entry in the second row. There we go. Let's do the second column. So we have row 2, that entry is 1, minus 2 times row 1, that entry is negative 3. So 1 minus 2 times negative 3 is 1 plus 6, which is 7. And we go ahead and we put that as the second entry in that second row. Again, let's do the third column. So hopefully you're getting the hang of this. It's 8 minus 2 times negative 3, which is 8 plus 6, or 14. And we go ahead and we pop that in for the third entry in the second row there. Okay, and notice that this augmented matrix has a linear system that corresponds to that second linear system on the upper right over there. X minus 3y equals negative 3, 7y equals 14. Okay, so that was our row replacement operation, our third elementary row operation. Okay, to summarize, we have three elementary row operations. We have an interchange. We can interchange any two rows. We can scale. We can multiply all entries in a row by any non-zero constant. And we have our row replacement operation where we can add to one row a multiple of another row. We say that two matrices are row equivalent if there is a sequence of elementary row operations transforming one matrix into the other matrix. And finally, if the augmented matrices of two linear systems are row equivalent, then it follows that the two linear systems have the same solution set.